Behind the power of every machine, there's a silent force at work: gears. From the vehicles we drive to the energy that powers our homes, gears transform speed into strength and motion into progress. They are the unsung heroes of modern engineering. But there's one place where they play an especially critical role: power generation. And today, we're taking you inside a gear system built just for that. We set out to design, build, and test a gear system that mimics the power transmission in real wind turbines. Wind turbines need to take slow, wide blade rotations and speed them up to generate power. That's where gearboxes come in. A typical turbine uses a gear ratio of about 30:1, and that's exactly what we designed a model off of. Spur gears, as it is illustrated in figure 13-1, have teeth parallel to the axis of rotation, and are used to transmit motion from one shaft to another parallel shaft. Of all types, the spur gear is the simplest, and for this reason will be used to develop the primary kinematic relationship of the tooth form. We used a two-stage spur gear system, one set 100:17 ratio and another with an 80:17 ratio, multiplying together for a total ratio of approximately 2.77:1. That means for every one rotation of the turbine blades, the motor spins 30 times faster.
To make this happen, we investigated the geometry of gears, profile, pressure angles, tooth profiles, addendum, and dedendum. We selected a pressure angle of 20 degrees as it is an industry standard. Equation 13-11 was used to determine the minimum number of teeth on the pinion without interference, which was determined to be 16. Therefore, to allow for error, we selected 17 as the number of teeth. An addendum coefficient of k equals 1 was chosen based on the available gears with 17 teeth in the catalog. An addendum of 1 mm and a dedendum of 1.25 mm was chosen based on table 13-1. A pitch diameter of 17 mm, 80 mm, and 100 mm was chosen with a diametral pitch of 1 mm based on the gears available in McMaster-Carr. Lastly, a root fillet radius of 0.3 mm was chosen. Once the design was completed, a contact ratio of 1.02 was calculated, which is below the 1.2 minimum threshold. However, for a real-world wind turbine, the gears will be much larger. This would increase the line of action, thereby increasing the contact ratio. Upon searching for these criteria in McMaster-Carr, the gears you see here were selected. And due to availability on McMaster-Carr, a perfect 30:1 ratio was not possible on the scale of our gearbox. We brought the McMaster-Carr gears to life by 3D printing the PLA gears with a custom housing. Thank you.